Hello, everyone. Welcome to the ILTA Physics online lecture. Today, we're going to start a new topic called impulse. Impulse is a concept we use a lot in our daily lives, and it refers to a physical quantity like the force two objects receive when they crash into each other. We're going to take a close look at this, step by step, from the perspective of dynamics. To put it simply, we want to quantitatively analyze a situation from a physics standpoint, like the image on the bottom right where a baseball player hits an incoming ball with a bat. The flying baseball and the swinging bat can both be explained by the motion of objects separately we've learned so far. The incoming baseball can be interpreted as linear accelerated motion, and the swinging bat can be seen as circular motion centered around the body. But how should we interpret the motion when the baseball and the bat actually hit each other? That is the big theme of what we are about to study. In other words, we want to analyze cases where two or more objects interact with each other while in motion. To do this, let's first think about the difference between the motion of a single object and the motion where multiple objects interact. We'll look at the physical characteristics of a collision, which is a classic example of interaction between multiple objects. Next, we'll look at impulsive force, the force acting during a collision, and the impulse that causes a change in the object's motion. All right, shall we go analyze the motion of multiple objects instead of just one? Up until now, we have analyzed the motion of a single object from a kinematic perspective. Physical elements like position, velocity, and acceleration of a moving object were key to interpreting its motion, and we've been analyzing that motion by representing the object as a particle model. Let's think about the motion of a baseball flying at 60 kilometers per hour and a car driving at that same speed, as shown in the image below. From a kinematic perspective, both objects can be represented as a motion diagram indicated by a single dot. Therefore, we could think of the motion of these two objects as being the same. But now let's imagine these two objects crashing into a wall standing right in front of them. Intuitively, we know that the two objects will show very different results after the collision. They were the same motion, but were they really the same? If the results after the collision are different, we're going to need a new concept or element of motion to explain that difference. That is momentum, which is the major theme of this chapter. So let's start studying the physics concepts for analyzing motion where multiple objects interact, like a collision, one step at a time. From now on, we're going to focus on the motion of objects when multiple items interact with each other. Specifically, we'll divide the timeline into before and after the interaction to analyze how the motion of each object changes. The representative physical phenomenon that causes this change in motion is a collision. In physics, a collision refers to an interaction where a large force acts between two or more objects for a relatively very short period of time. As you can see in the image below, a common example of a collision is a billiard ball hitting another ball and both moving off in different directions. Or we can imagine two soft objects moving toward each other, colliding, merging into one, and stopping right there. We are going to analyze these types of collision movements from now on. Among the general characteristics of a collision, the collision time gets shorter as the objects get harder. A good example from earlier is how the collision time of hard billiard balls is relatively shorter than the collision time of soft objects. In the case of these collisions, our goal is to analyze the motion of each object before and after the impact. In other words, we'll use the new concept of momentum to interpret how the speed and direction of an object change from before the collision to after the collision. In a typical collision process, the force applied to the objects is called impulsive force. This kind of collision usually happens over a very short time interval. Think of the force applied when hitting a nail with a hammer or hitting a baseball with a bat. The image below shows a classic example of a collision. A high-speed camera sequence of a golf club hitting a golf ball. The left image is the moment the club and ball first touch, and the middle one is the moment of maximum compression as the ball deforms. The last photo is the moment the ball regains its shape and moves forward. In this process, the effect of the force the golf club exerts on the ball is proportional to two factors. Naturally, it's proportional to the force the club exerts on the ball. We call it the impulsive force. And it's also proportional to the time interval that the golf club and ball are in contact. This is exactly why coaches emphasize following through when you swing a golf club. If we express the impulsive force I just explained with the golf example more scientifically, it looks like the graph on the right. When we put time on the x-axis, you can see that the magnitude of the force exerted by the golf club on the ball follows a bell shape. Using this graph to think about the effect of the force applied to the ball, we find it's proportional to the area of the gray region. We call this impulse. This is because the area of this region represents a physical quantity that accounts for both the force of the impact and the duration of the collision I just described. Pay attention here. You should understand impulse as the effect of a collision that takes into account both the impulsive force applied to the object and how long it lasted. Now, let's study this impulse quantitatively on the next page. Let's look at the golf club and ball example again. We call the total force exerted by the golf club on the ball during the collision the impulse, and we define it as being equal to the area of the gray region in the graph below. In a typical collision, the impulsive force applied to an object during the time interval might not be constant. Therefore, by using a constant average impulsive force, we can calculate the impulse as the product of that average force and the collision time. Please remember that the unit for impulse is the product of force and time, based on the definition. Naturally, impulse is a vector quantity that has a direction, and that direction is the same as the direction of the impulsive force. This relationship for impulse carries a very important physical meaning. In everyday life, a car's airbag takes a certain amount of impulse generated during a crash and uses the cushion to increase the collision time between the person and the car body. By doing this, it serves to reduce the impulsive force acting on the person. As another application, if you increase the collision time between the bat and the ball through a follow-through during a baseball or golf swing, you can create a larger impulse even with the same amount of force, allowing you to send the ball much further. Finally, the impulse we just discussed is a crucial concept in collisions and is closely related to the change in momentum that we'll study in the next lesson. I mentioned impulsive force and impulse so much in today's lecture. Is it a bit confusing? To sum it up, just remember that impulsive force is the actual force applied to the object, while impulse is the product of that force and the collision time, representing the overall effect of the collision. They might be unfamiliar terms and concepts for now, but if you understand them well from the start, I expect you'll be able to grasp the physics of collisions much more accurately. That's it for today's lecture. Great job, everyone. I'll see you next time.